Have you ever wondered how computer programs simulate real-world objects and their behaviors? It's fascinating to think about how a few lines of code can mimic the complexities of the real world. Imagine designing a racing game. You need cars, right? But not just any cars, cars that can accelerate, brake, and even change colors. But how do you represent these cars in code? How do you make them behave like real cars? That's where object-oriented programming, or OOP, comes in. It's a paradigm that helps us structure our code in a way that mirrors real-world entities. OOP is a powerful programming approach that allows us to model real-world entities as software objects. These objects can have properties and behaviors just like their real-world counterparts. Just like a real car has properties like color and speed, and methods like accelerate and brake, we can define similar attributes and functions in our code. We can create car objects in our code with similar characteristics. These objects can interact with each other, making our programs more dynamic and realistic. OOP helps us write cleaner, more organized and reusable code, making it easier to build complex software applications. It promotes better design and maintainability. This essay will guide you through the fundamental concepts of OOP, providing clear explanations and practical examples along the way. You'll learn about classes, objects, inheritance, polymorphism, and more. Get ready to unlock a powerful way of thinking about and writing code. By the end, you'll have a solid understanding of how to bring the real world into your code. Imagine building a house without a blueprint, just stacking bricks randomly. It would be chaotic, inefficient, and probably result in a structure that's unstable and unsafe. That's what programming without OOP can feel like: messy and disorganized. Without a clear structure, your code can quickly become a tangled mess, making it hard to maintain and debug. OOP, or object-oriented programming, provides a structured approach, allowing us to organize code into reusable modules called classes and objects. This method helps in breaking down complex problems into manageable pieces. Think of a class as a blueprint for creating objects. Just like a blueprint for a house, a class defines the structure and behavior of the objects created from it. For instance, a car class defines the properties and behaviors that all cars share. This could include attributes like color, model, and speed, as well as methods like start, stop, and accelerate. Objects, on the other hand, are instances of a class. They are the actual entities created using the class blueprint. So you could have a red Ferrari and a blue Tesla, both instances of the car class, each with its unique values for properties like color and speed. Despite their differences, they share the same underlying structure. This structured approach makes your code more manageable, especially for large projects. It allows multiple developers to work on different parts of the project simultaneously without stepping on each other's toes. Plus, it promotes reusability. You can use the same car class to create different types of cars without writing redundant code. This not only saves time, but also ensures consistency across your project. By organizing your code with OOP, you can achieve a cleaner, more efficient, and scalable code base, making your development process smoother and more enjoyable. Let's dive deeper into the core components of OOP classes and objects. These are the fundamental building blocks that allow us to create complex and reusable code structures. Imagine you're building a virtual zoo. This zoo will be a digital representation of a real-world zoo, complete with various animals and their unique traits. You'll have different animals, each with unique characteristics and behaviors. These animals need to be represented in a way that captures their individuality while also sharing common traits. A class is like a blueprint that defines the structure and behavior of similar objects. It serves as a template from which individual objects are created. For instance, you could have an animal class that outlines common properties like name, age, and methods like eat and sleep. This class acts as a general template for all animals in your zoo. An object, on the other hand, is an instance of a class. It is a specific realization of the class blueprint, with actual values assigned to the properties. It represents a specific entity created based on the class blueprint. Each object can have different values for the properties defined in the class. In our zoo example, you could have a lion object named Simba, age 5, and a giraffe object named Gigi, age 3. These objects are instances of the animal class, each with its own unique data. This approach allows us to model real-world entities in our code, making it more intuitive and organized. By using classes and objects, we can create a structured and maintainable code base that mirrors the complexity of the real world. Think of a class as a cookie cutter. It defines the shape and size of the cookie, but it doesn't bake the cookie itself. Similarly, a class in programming defines the structure and behavior of objects, but it doesn't create the objects themselves. Let's create a simple dog class, Python class dog_def, self-name breed, self.name equals sign name self.breed equals sign breed def bark self, print woof. In this example, our dog class has properties like name and breed and a method called bark. This class acts as a template for creating dog objects. Section 5. Objects, instances of a class. Now let's create some dog objects using our dog class. My underscore dog equals dog, buddy, golden retriever. Your underscore dog equals dog, Lucy, poodle. We've created two dog objects, my underscore dog and your underscore dog, each with its unique name and breed. We can access their properties and methods using dot notation. Print my dog dot name, output buddy, your dog, bark, output woof. Just like real dogs, our dog objects have distinct characteristics and can perform actions. Section 6. Inheritance, building specialized classes. Inheritance is one of the most powerful features of OOP, allowing us to create new classes based on existing ones. Think of it like a family tree. Children inherit traits from their parents. Let's say we want to create a cat class. Instead of defining all the properties and methods from scratch, we can inherit them from our existing animal class. Class cat, animal, def, self, name, age, breed, super, name, age, self.breed equals sign, breed, def, meow, self, print, meow. Our cat class inherits properties like name and age from the animal class and adds its unique breed property and meow method. Section 7. Benefits of inheritance, reusability and organization. Inheritance offers several benefits, making our code more efficient and organized. Code reusability. We can reuse existing code from parent classes, reducing redundancy and saving time. Improved organization. Inheritance helps create a hierarchical structure, making our code easier to understand and maintain. Reduced development time. By reusing existing code, we can develop new features and classes more quickly. Inheritance is a fundamental concept in OOP, promoting code efficiency and organization in large software projects. Section 8. Polymorphism, many forms, one interface. Polymorphism means many forms and is a key concept in OOP that allows objects of different classes to be treated as objects of a common type. Let's say we have a shape class with a method called calculate_area. We can create subclasses like circle and rectangle, each with its implementation of the calculate_area method. Now we can use a single line of code to calculate the area of any shape object, regardless of its specific type. Shape, calculate, area. Polymorphism simplifies our code and makes it more flexible, as we can work with objects of different classes through a common interface. Section 9. Encapsulation, protecting data and ensuring integrity. Encapsulation is like a protective shield around an object's data, ensuring that it's accessed and modified in a controlled manner. Think of it like a bank vault. You need the correct authorization to access the valuables inside. In OOP, we achieve encapsulation using access modifiers, private properties. These properties can only be accessed from within the class itself. Public methods. These methods provide controlled access to private properties, allowing us to get or set their values while enforcing validation rules. Encapsulation protects our data from accidental corruption and ensures data integrity by enforcing validation rules through public methods. Section 10. Mastering OOP. Your journey begins. Congratulations on taking your first steps into the world of object-oriented programming. You've learned about the core concepts of OOP, classes, objects, inheritance, polymorphism, and encapsulation. Remember, the key to mastering OOP is practice. Start by creating simple programs using classes and objects. Experiment with inheritance to create specialized classes. Explore polymorphism by using common interfaces for different object types. As you gain experience, you'll appreciate the power and flexibility that OOP brings to software development. Section 11. Next up, design patterns. Level up your OOP skills. Ready to take your OOP skills to the next level? Stay tuned for our next topic, where we'll delve into the fascinating world of design patterns in OOP. Design patterns are reusable solutions to common programming problems. They provide proven approaches for designing flexible, maintainable, and scalable software applications. Get ready to unlock a new level of expertise in OOP.